exponential growth and decay functions. Exponential growth parent functions. So growth, ab to the x, happens when your b value, your rate, which is called the growth factor, is greater than 1. So what happens is if you look at the graph, it increases as you move from left to right. Now, these exponential functions have an asymptote at y equals 0. That means that that's a boundary that this graph is not going to cross. So right here at y equals 0 on the x-axis, there is an imaginary boundary line. That means that my function will never reach negative y values. Then, exponential decay, y equals ab to the x, is when your b value is between 0 and 1. Basically, it's smaller than 1, but not negative. We call this a decay factor this time because it's an exponential decay. That means from left to right, your graph is decreasing. Your y values are going down when you move left to right on the graph. Just like the exponential growth function, this also has an asymptote at y equals 0, which means the exponential decay function will never reach negative y values either. So let's talk about graphing these exponential functions. There's a few steps. So identify the value of the base. This will tell you if you have exponential growth or decay. So if you are increasing from left to right or decreasing from left to right. Then make a table of values. So the domain is all real numbers. That means I can have any x I want, but I need to be sure to include negative and some positive x values. Once I have my table, plot the points. Then step forward, draw the graph from left to right, but don't forget about the horizontal asymptote at y equals 0, meaning we're not going to go underneath the x-axis. So example 1, tell whether the function below represents exponential growth or exponential decay, then graph the function. So we have y equals ab to the x. Well, the b value is a 2, and 2 is greater than 1, so that means we actually have exponential growth. So that means our graph will be increasing from left to right. So since we're increasing from left to right, I want more positive values than negatives as far as the x's go. So I only have 2 negatives and I got more positives because that's where the majority of my graph is going to be. So now that we know what our domain is going to be, we need to figure out our range. We need to find those y values. So we're going to take each x and substitute. So the first one is y equals 2 to the negative 2 power. Use some kind of calculator to help you with this, and that's going to give you 0.25. So that's the first value in my table. Then we're going to take 2 to the negative 1, which is going to equal 0.5. That's our second value. Then we want 2 to the 0, which is a 1. Then we want 2 to the first, which is 2. 2 squared, which is 4. And then 2 to the third, which is 8. So now that we have a pretty good value of tables, we're going to plot these values on our graph. Make sure you're looking at the scales that we're given. So our x's are going by 1s and our y's are also going by 1s. 1, 2, 3, 4. So when we plot these values, negative 2, negative 0.25 is going to be close to my axis. Negative 1 half, 0, 1, 1, 2, 2, 4, and 3, 8. When we connect this, remember we need to not forget about our boundary line, our asymptote at y equals 0. So our graph gets really close to the axis from left to right and then increases, moving left and right forever. And there's the graph of y equals 2 to the x. Example 2. Tell whether the function below represents exponential growth or exponential decay, then graph the function. So again, our general layout is y equals ab to the x. So b is that 1 half. So we have 1 half, which is smaller than 1. So in this case, we have exponential decay, which means our graph is going to be decreasing from left to right. Now I don't have the x values pre-filled in this time. So since these are moving from left to right and it's decreasing, that means your higher y values are on the negative end of your x. So I want more negatives than I do positives. Now that I've chosen my x values, we're going to find the y values by substituting. So y equals 1 half to the negative 3, which is going to give us 8. Y equals 1/2 to the negative 2, which is going to give us 4. If you notice, this is just the opposite of the other table. That's not always the case, though. If I had done something like maybe 1/3 to the x, that's going to give us a different values. Y equals 1/2 to the 0 is a 1. Y equals 1/2 to the first is 1/2, or we're going to think of it as 0.5 because sometimes decimals are easier. And 1/2 squared is 0.25. Now that we have our values, let's go plot them on our grid. So we have -3, 8, -2, 4, -1, 2, 0, 1, 1.5, and 2.25. And we also can't forget about our horizontal asymptote at y equals 0. So when we graph this one, we're going to decline from left to right, but we're not going to cross the x-axis. We're just going to get very close to it. And there's the graph for y equals 1/2 to the x. Exponential models for real-world applications. So we use an exponential model when these real-world applications increase or decrease by a fixed percent each year or some other time period. So there's two models we use. We use an exponential growth model, is if we have a percent increase, which of course we write as a decimal. The equation for that is y equals a, which is the initial, times 1 plus r to the t, and r is your rate. Then the exponential decay model is exactly the same, but it's 1 minus r instead. So if you're increasing, we're going to do 1 plus r. If you are decreasing, we do 1 minus r. And again, a is the initial, and r is the percent decrease written as a decimal. So example 3. The population P in thousands of Austin, Texas during a recent decade can be approximated by y equals 494.29 times 1.03 to the t, where t is the number of years since the beginning of the decade. So letter A, is this situation exponential growth or exponential decay? So in this one, they already gave us the equation. Now, the way we figure out growth or decay is we look at that b value. So in this example, b is equal to 1.03. So because 1.03 is larger than 1, that means this is exponential growth. If you had a b value that was smaller than 1, it would be exponential decay. Letter B, identify the annual percent increase or decrease. So this again is looking at b. So b is supposed to be 1 plus or minus r. We already said this is growth, so it should be 1 plus r. So this is asking us what was r in order to give us that 1.03. Well, 1 plus what is 1.03? Well, that's going to be 0.03. So r is equal to 0.03. But it wants a percent increase. So we're going to have to change this r back to a percent, which means moving this decimal place 2 times to the right. So the percent increase was 3% increase. Then letter C, estimate the population in 10 years. So we're going to use the model it gives us, the equation, and we're going to estimate the population after 10 years. So this is what t is equal to. So we're going to take the equation they give us, so y equals 494.29 times 1.03 to the 10th power, and we're going to evaluate. So with the help of a calculator of some kind, we're going to evaluate this 1.03 to the 10th, and we end up with 1.34. Then we can multiply 494.29 times 1.34 to get 664.28 thousand people, because it said in the very beginning that the population was in thousands. Example 4. You take 325 milligram dosage of ibuprofen. During each subsequent hour, the amount of medication in your bloodstream decreases by 29% each hour. Letter A. Write an exponential model giving the amount y in milligrams of ibuprofen in your bloodstream t hours after the initial dose. So this is where I need to write the equation in the format y equals ab to the x. So the initial, that's my a, is how much of this medicine was in my bloodstream when I took the medicine. So it said I take a 325 milligram dosage. So a is equal to 325. Now b takes a little effort. So first thing we have to figure out, are we increasing or are we decreasing? So it says the amount of medication in your bloodstream decreases by about 29% each hour. So since we are decreasing, my b is going to be 1 minus r. Now the r is that 29%, but I need that 29% written as a decimal. So 29%, take the decimal point at the end of 29, move it 2 times to the left. So what we're actually using is 0.29. So my b is 1 minus 0.29, which is 0.71. So this is the b value that we're going to be using in our equation. So we have y equals a, which is 325, times my rate, which is 0.71, to the x power. Now letter b, estimate how much medicine will be left in your bloodstream after 6 hours. So 6 hours, that's my x or my t, whichever variable you used. So we're going to take these 6 and substitute it into the original equation. So y equals 325 times 0.71 to the 6th. Again, use the calculator of some kind to estimate 0.71 to the 6th. Y equals 325 times 0.128. And then 325 times 0.128 is about 41.633 milligrams. Now, if this was a percent increase situation, back at the top when we did 1 minus, we would have actually done 1 plus. So decreasing situations do 1 minus the rate, increasing situations will do 1 plus the rate. Now let's talk about some compounded interest. So this happens with usually like bank accounts. So consider the initial principal P. So what that means is that's the initial amount. So this P is the initial amount deposited into the bank account that pays an interest at an annual rate R expressed as a decimal. So R is the interest rate that is compounded n times per year. So this n is how many times a year you're being compounded. Compounded per year. So let's talk about that for just a minute. So if you are compounded, let's say yearly, well, how many years are in a year? Well, that would be 1. So your n would be a 1. If you were compounded daily, how many days are in a year? 365. So that would be your n. Let's say you're compounded weekly. Well, how many weeks are in a year? That'd be your n of 52. If we say we are compounded quarterly, well, if we divide a year into quarters, that means your n would be a 4. And then the last one that's most common is monthly. If you're compounded monthly, that means you have an n value of 12. It's basically how many of those increments can you fit into a year. That's how you can figure out what n is. And then it says the amount A in the account after T years. So A is actually your final amount. That's usually what we're looking for. And T is the number of years you're doing this for. So maybe I want to leave the money in the account for 2 years, 8 years, half a year, however long we want to leave the money in the account. So let's talk about an example. You deposit $9,000 into an account that pays 1.4% annual interest. Find the balance after 3 years when the interest is compounded quarterly. So first, let's find all of our pieces. So it says you deposit $9,000 into account. That means that principal, the initial, is $9,000. Then it pays 1.46% annual interest. That's that R. But we can't use 1.46%. We need to change that percent to a decimal. So move the decimal point 2 times to the left. So R is actually 0.0146. Now it says find the balance after 3 years, so that will eventually be T, when the interest is compounded quarterly. So compounding quarterly means your N is going to be a 4. So let's write down the original equation. A equals P times 1 plus R over N to the T. So let's write the general equation first, then we'll figure out the balance after 3 years. So the general equation, the P is going to be the $9,000 that you originally put in the account, 1 plus the R as a decimal, the rate was 0.0146. The N is compounded quarterly, so it's a 4, and then to the T. So this is the general equation that you can use for this account after so many years. So I can plug in different values of T and find out the amount that comes out. Well, it wants a specific of 3 years. How much money will be in this account after 3 years? So now we're going to take this equation and substitute in a 3 for T. And we're going to evaluate. So use your order of operations to make sure you evaluate this in the right order. So I need to get this inside the parentheses stuff as simple as possible. So I'm going to do first the 0.0146 divided by 4. So 0.0146 divided by 4 is about 0.00365. Then I need to add 1 plus 0.00365, which is just 1.00365. Now I can use the exponent. So I'm going to take 1.00365 to the third power. So we get 9,000 times 1.012. And then finally I can multiply these together. So 9,000 times 1.012 is 9,098.91. So this is the amount of money in the account after 3 years with this interest rate and compounded quarterly.